Max, I'm going to be going over all of the exam questions from the Spring 23 Physics 2 exam. First thing I will note before we actually jump into the questions is that because it's multiple choice, anytime there's a metric unit, so 10 to the, whatever, I'm not going to convert it. My answers might be off in terms of magnitude, so I might get like 0.985 instead of 98.5, but you'll be able to recognize those as the correct answer because it's multiple choice. All right, let's start. Oh my goodness. Let's start with number 1. So on the x-axis, we have a charge, at -1 centimeters with a charge of 9, and a charge at 0 centimeters with a charge of -4. And we place a charge such that it's equalized. So the first thing you want to check in this scenario is what happens if you place it in the middle. In the middle, we have opposing charges, so it'll either move very strongly in one way or the other, which we don't want. So we want to place it on either side. Now, this charge is stronger, which means we want to place it on this side here. So we're essentially going to be, this is 0, we're solving for the x-coordinate here. And the way we can just do that is by using the Coulomb's law here. The actual charge and k are inconsequential. We just want to set these equal to each other. So we have 9 over 1 plus this x. This line here is our x. 1 plus x should be equal to 4 over x. Because we don't use a -4 because it would have been a -4 over here and we just push it to the other side. So we want them to be equal. And you can just throw them to your calculator. Actually, this has to be squared. And when you throw this into your calculator, you will get x equals 2, which is correct. All right, number 2. So we have a square here, -4, 2, and 1, with side length 3. What is the x component of the force on Q3? So we just need to consider this here and this here. So the force because of Q2 here, it's just going to be 2 times 1 over 3 squared. And the component here, it's going to be minus 4 times 1 over, the distance is 3 squared plus 3 squared, right? And this is normally square rooted, but it's squared all, so we can just leave it like that, and we multiply by k. When you multiply that all out, 2 over 9 minus 4 over 18. Oh wait, that's 0. Oh yes, of course. Because this is a 45-degree angle, we have to include cosine of 45 here as well. Times cosine 45. Multiply that by k, which again, since I'm not doing any fancy stuff, that's just going to be 9, and I ended up getting 0.585. We know that this is the same value, incorrect magnitude, but that's fine. So that's correct. Okay, number 3. So we have a shell, which instantly should kind of bring the shell theorems to mind. Radius 2 and a charge were placed from it. What's the magnitude of the force on the point charge? So for anything that's outside a sphere, we can just model the sphere as a point charge here with the same charge, which would be 6. Its R here is 2, and it's got a D of 1. And at this point, it's just Coulomb's law, 2-point charges. We have this is 2, so it's 6 times 2, it's a multiplication, over the radius, which is 3 squared, times k, which again, k is, we're just taking as 9. These cancel, it's going to be 12. Again, incorrect magnitude, we get it. 12 is just times 10 is 120. All right. Magnitude of the electric field at the other vertex of this triangle, P here. We got two positive charges here. And here we just want the electric field, which means it doesn't matter what the charge of P is. So this is 4, and then we got 6 meters here and here. Again, this is just going to be very much Coulomb's law adjacent. This is the exact thing we're doing. We'll have to do the x first, so let's do the x first. The x is going to be this charge here over 6 squared times k plus this charge here. Now it's quite similar. We get 4 over 6 squared times k, but this is actually a 60-degree angle because it's an equilateral triangle. And so for the x, we have cosine of 60 there as well. So that's going to be our x component here. And then we need our y component, which is just going to be this kind of leftover part here, k sine of 60. All right, and then we square both of those, add them, square root the result. 4 over 36 times 9 plus 4 over 36 times 9 times cosine of 60 is that squared. Am I doing this right? I don't remember these being the numbers I got earlier. But oh wait, oops. In an electric field, you do use K. What was I doing? Am I crazy? I don't know. My notes don't have me using K, but that can't be right. Surely that can't be right. And then 4 over 36 times 9 times sine of 60 is that. Square it. That's that. Bum, 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 bum. Yeah, okay, so you do use K. I don't know what my notes were doing, but essentially this becomes 2.25, and this becomes, or 1 squared, and this becomes 0.75, leading to 3 square root it. You get square root 3 here. All right. Yeah, I don't know, my notes don't have K. Okay, these ones, integral ones, annoying, but hopefully shouldn't be too bad. So we have a rod of length L and charge Q, and we're just at, between 0 and L. The magnitude of the electric field at a point on the x-axis where it's greater, where our total x is greater than L. So this is going to be essentially this integral, right? Where we have k, and then we integrate here from 0 to L on this continuous distribution. So here it says dq over r squared. That's a good starting point. Let's go there. dq over r squared. What the heck is d? Okay, no, sorry. dq. dq is just a small portion of charge, right? And since the entire thing is of length q, if we divide that by the length of the rod, that's like how much charge is in each unit. And we can call this dx, will probably be easiest. But yeah, we essentially get a unit of charge and then a small length of that charge. So also r squared. R is equal to this x0, where we're at, x0, minus like how far we've gone into the rod already, which is just the x here. So what we can just do is we can transform it to look a little bit more q over L. This should be x0 minus x squared dx. And you can see here, this -2 is just squared in the denominator. And yeah, we got everything there. Yeah, the integral ones can be daunting, but what the heck's happening here? Don't be too intimidated by them. Okay, this one it's written a little poorly. This is a electric field that forces the electron downwards. So I think it's the field's actually going upwards, which the electron goes the opposite direction, but it doesn't specify that. Oh yes, it does. I'm stupid. Whatever. Anyways, we have a initial speed of an electron at an angle. It will be moved downward due to an electric field, and it will hit the screen eventually. First thing we do is we need to know at what time does it hit the screen. So we can use the equation for an x at any point. So the x is 3 when we are interested in it. And the only thing that's affecting it is the x velocity, because y velocity doesn't change. The x velocity doesn't change. We don't have an x acceleration. So we can just use 5, and then this is 30. We want the cosine here for the x. So cosine of 30, and then times t. And if we do that, just 3 divided by 5 divided by cosine of 30, we can get that t is equal to 0.693, at which point we can then solve for the velocity when it hits the screen at this, which we know is at this time. So the velocity, and keep in mind this is asking about the y component, so the initial velocity would actually be 5 times sine of 30, and it's also getting reduced at a certain rate. Now, what is a rate? Well, in order to do that, first remember from physics 1 that force equals mass times acceleration. We also have another thing, a force here. Force is equal to charge times electric field. Putting that together, we can see that acceleration is equal to charge times electric field over mass. Now, that just means that when we're doing this, right, normally we have an AT squared over 2. A is in fact this value, this QE over M. And then we're doing it on an electron, so we have to use the electron constants, which is a little bit annoying. I just probably say, plug this into your calculator, right? 5 times sine of 30 minus, what are we at? So charge of an electron, let's see, is 1.6. Or actually, this is only t, sorry, because this is on the velocity, times 0.693. Actually, I got a little distracted there. We got to do the electron field times 4, times 4. Then the mass of the electron, which is given here, 9.1, and then divided by not 2. That's also not applicable here. But yeah, we get 2.01, which again it's just 2. Yeah, 2.01. All right. Ooh, this one's I do like these ones. Rank the magnitude of the electric field at the center of the square. Remember that the electric field has a direction to it, and if you have like these same charges on both ends, they will either both attract in the same direction or both repel in the same direction. So effectively, these two will cancel each other out. Same here, right? Here you have a double force in the same direction. It could be in that direction. It could be in this direction. The important thing is the two electrons are kind of working together. So that's good. Here, these two cancel, and then we have a double force. And then all 4 of these cancel. So A and D are the lowest, then C, then B. A and D, C, and B. Okay, perfect. Now, this one, you got to read this carefully. This is asking for the electric potential. Now, the thing about the electric potential is it does not care about the actual direction. It just cares about the actual value of the charge, since all the radii are the same. I assume it does care about the radius. No, maybe not. I don't know. So what we see here is we have a plus 1, a plus 1. So we have 2, and then minus 1, minus 1. So this is a total of 0. But then here, where we normally had our very high electric field, we get plus 1, minus 1, minus 1, that's 0. Plus, 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 minus, that's 1. And then plus, 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 that's 4. So D's potential is the highest than C, and these two are stuck at 0. Okay, spherical conducting shells centered at the origin. So based on the flux, what is the charge on the inside surface of the outer shell? Okay, so what we can observe here, remember that we'll have two shells. I'll just there's one, there's the other, right? Inside is just going to be 0. There's no point that's changing that. And inside the actual shell, since they're conducting, it's also the field's always 0. Now we can see that here the flux becomes higher, and that is due to the fact, because remember, flux is relatively equal to the charge enclosed. There's a formula here which is important. So we know that the past, this point is all 0, right? The charge enclosed is 0. But when we get to this point here, the charge enclosed increases. So we can say that this has that 3 flux associated with it, this surface of the conductor, because remember, only the surface of the conductor will have charge. That inherently means that this conductor, because we're trying to, this will induce a force in this conductor, will have a force of -3 in it. And that's what creates this 0, right? Because now in this circle, you have a charge enclosed of 0, which makes this 0. And then it adds this -2 out here to have this full charge enclosed of -2 here. But we want the charge on the inside surface. Now, the charge enclosed is actually equal to the flux times epsilon 0. So we take a -3 and multiply by epsilon 0, which I think is 8.85 times -3, -26.55, close enough to -2.7. Okay. Two uniformly charged thin spherical blah 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 are centered at the origin. So we have a shell with radius 3 meters, and we have a shell with radius 5 meters. Net charge -4, net charge 6. What's the magnitude and direction of the field right here at r equals 4 meters? Now, first thing to note is that the outside shell we don't care about, because it's, again, electric field in a shell doesn't matter. So we can completely simplify this problem into just being this shell of radius 3 with a net charge of -4 and, this point here. So let's see, what do we do here? Oh, the next problem's annoying. So this, we can just use the charge enclosed here, because we know that the net charge of the shell is -4, so we know that the charge enclosed here has to be this -4. And we are trying to find the electric field, and if you see, this is actually equal, charge enclosed is equal to epsilon 0, electric field times the area. Now, epsilon 0, then electric field, which we're solving for, then the area. This is talking about the surface area of what we're doing. The surface area of a sphere, I believe, is 4 pi r squared. And we are given the r here as 3. Basically, let's plug that into the calculator. So we're trying to solve for e here. So we go -4 divided by 4 divided by 8.85 divided by pi divided by 9 and we get something that is wrong, because this R is actually the magnitude of the R at the Gaussian surface. You don't plug in 3 here, you actually plug in this 4, the 4 of the Gaussian surface, and that'll give you, I got negative 0.00225. So you get this. It is pointing inwards because the electric field, what is it? It always points positive to negative, and the inner sphere has a negative charge, so it'll point inwards. This one's really annoying. I don't like this question. But the idea is you have a solid sphere of radius r and a density rho. First of all, the electric field, when is it going to be maximized? Well, when it's inside the sphere, the electric field is really only like represented by the surface inside the sphere. By the charge, it's proportional to like the charge enclosed here. But also when you get further away from the sphere, the distance kind of like creates a fall off in the electric field. So the maximum is actually right here, like nestled up against the sphere. And what that electric field would actually be, well, you can, I think you just like use the formula similar to what we did above. We have the charge density. We can use it to get the area, but essentially, charge enclosed, it's going to be equal to the charge density times the volume of the sphere, which is 4/3 pi r cubed, or rather, big R, that's a B, big R cubed. And when you solve for that, and then that's in turn equal to the epsilon 0 times the electric field times the area of your Gaussian surface, which is, if you're nestling up against it, is just going to be 4 pi r squared. And effectively, you'll see like the electric field, what it's equal to rho over 3 over epsilon 0 over, or times r. And honestly, I think the easiest way to solve this question, it's multiple choice. There's only like a few possible combinations, is to like plug everything into this equation with like the adjusted a and seeing what you can get. Or you'd also have to adjust q if you're going inwards. But the idea is kind of that when you like look at between these two, so if you the only thing that really matters is like these r's, right? And the r here is more so like a little r, because it's dependent on the actual surface you're making and not the max surface here. So the electric field will always be proportional to the big R cubed over the little r squared. But the max R, and then, if you multiply this by the max R, which is like R over 2, you can like solve it and you'll get like R equals root 2R. But honestly, I would just plug this stuff in, because okay, number 12. This is just a flux problem. Same equation we've been using, right? We want the charge, which we're given, or we're trying to find like surface charge density, which is this sigma, and the charge enclosed will just be equal to the sigma times the area of that infinite plate. Again, we won't have to actually worry about like what that entails, thankfully. And that's equal to epsilon 0 times flux. Now, what is flux? Flux is the net like amount of electric field. So it's the amount going out minus the amount coming in. So for this, if we're trying to solve for the surface density of plane 3, we got 3 coming out and 2 coming in, which means the flux is going to be like 1. And this electric field is also multiplied by the area, which means that the two areas cancel, and we just get that epsilon 0 is equal to the surface charge density, which is what we see here. All right. This one, this moves on to electric potential. This is one of these two equations here. These four, I don't know. The idea here is that you have a V final and a V initial. So how do you calculate the difference there? Well, you go minus from 0 to 5. We're going to integrate over dy. You do the electric field, ds technically is what it is. But the electric field is 3I plus 4j. Now, I got confused when I was doing this the first time. This is, despite the i's and j's, like this is a constant, right? So when you integrate it, what you end up just getting is 5 times 3I plus 4j. However, the even more confusing part here is that this 3I, that's like stuff that's heading in the x direction. And when you integrate over the y, you only care about the electric field in the y direction. So you multiply these two numbers together, and that ends up giving you the 20 that's in the answer. Now, why negative 20 and not positive 20? Because of this negative sign here. I just forgot to include it here. Okay. This one uses these three equations here, where essentially electric field is the derivative of the voltage. The difference in voltage, I guess. But the idea here, you have this, and when you have this A for some reason as well. Magnitude of the electric field, right? You want to take x, y, z, square them up, square root them, add them, square root them. And each of them, so the electric field for x is just going to be the derivative of this with respect to x. Partial derivative with respect to x, which here is just going to be like a of 2x. All of these terms, they die out. They don't have an x in them. So a of 2x, it's also like a of 2y or a of 2z. So, you know, you'd end up just having like square root 3 times 2 times 1 squared plus 3 times 2 times 2 squared plus 3 times 2 times 3 squared. Put that all under square root, you get 22.45, rounds down to the correct answer, 22. This problem, it's weird. It seems hard, it's not as hard as you might think. So basically you have a capacitor here, one of them's loaded up like so, one of them does not have any voltage. Important thing to note, they give you this voltage. These are coulombs where you label them as like plus or minus charges. The coulombs are equal to the voltage times the farads. Basically, the capacitance. This is annoying. The charge is equal to the voltage times the capacitance. And since this is 1, you just multiply them, and it's going to be plus or minus 12. Basically, the switches are closed, and since both of these will have the same voltage in the end, but we got to know, based on their capacitances, how this 12 charge will distribute between the two. And ultimately, since the charge you have in a capacitor is just proportional to its capacitance, since this is 2 times bigger than this, it's going to get 2 times more charge. So out of the 12, this is going to get 8, and this is going to get, 4. So C1 is just going to have 4. All right. This one, let's rewrite this. Let's look this way, right? We encounter C1. So this is C1, which is 2. Then we continue looking. You can see we branch into both C2 and C3. So we'll have C2 here and C3 here. And then we join back up and end the circuit. So join back up, end the circuit. So this is our simplified diagram here. Now we have to combine, right? First, we take these two are in parallel, so they're now 4 coulombs. This is 2 coulombs, not coulombs, capacitance, farads, I guess. And then these are in series, so the sum is 1 over 1/2 plus 1/4, or 4/3 of a capacitance. And the voltage here, this applies for the whole thing, so this thing is 6 volts. Now, one thing that's not on the formula sheet, when capacitors are in parallel, like so, their voltages are the same and their charges add. When they are in series, like so, their voltages add and their charges stay the same. So first of all, the charge here, it's just the capacitance times the voltage is going to be 8 coulombs. And like I said, the 8 coulombs here will transfer, right? Both of them will be 8 coulombs. And then the voltage is dividing. So this is 4 volts, this is 2 volts. And then we have to move forward with this part of the circuit here. Like I said before, the charges add and the voltages stay the same. So this is 2 volts, this is 2 volts, and when you do the math, this is going to be 2 times 2, 4 coulombs for each of these. Bada bing, bada bing. Okay, parallel plate capacitor. This is very similar. It's just you treat it like one of these. The thing is, you just want to use this formula. Capacitance is equal to K epsilon 0 A over D. You want to calculate each of these capacitances individually and sum them up using these rules. So capacitance 1 is just going to be like K1 epsilon 0 A over D, which this D ends up being 1, and this is A over 2 for 10. So, 10 over 1 times 4, it's 40 epsilon 0. C2, it's, again, just K2 epsilon 0. A over D, the ratio remains the exact same for this one as well. You just have a reduced one here, so it's 20 epsilon 0, if I remember correctly, yeah. And then this part here, with no dielectric constant, it's just 1. So I'll call this part C3. You can just like ignore this. You're essentially just solving this. Here you have the same A over 2, but you have 2D, so you're dividing by 2. So it's going to be 10 over 2, or giving you 5 epsilon 0. And then basically these are in series here. So you would, take 40 multiplied by 8.85, take C2 20 multiplied by 8.85, and then you do the series calculation. So the new one is 1 over 354 plus 1 over 177. 118 is the whole thing here, 118. And then you would add that with the 5 times 8.85. Boom, boom. 162. Again, that's effectively the same as 16.2. Okay, getting close to the end here. Different materials. We're going into resistivity here. This sort of stuff. Different materials. Length, we're given the areas, the diameters, and we're given a current. So we're obviously going to be using this formula here since we're given resistivity. Doing this, we want energy dissipated, which is this this power formula here. So power is equal to, and the energy dissipated overall is just the energy dissipated here plus here. You should add them up. So power is equal to I, which we're given, right? We're given that, I'll do power of A first. We're we're given the current A. And then let's solve for the resistance, I guess. So I squared R. Now what is R? R is many things, but among them, this rho L over A. So rho L over A. So I know we're given length, we're given rho, we're given what have you. And one thing to note, I don't know why they always do this, it's the diameter. So this just becomes like pi. So you're going to have 9 times 4 times 3 divided by pi here for the resistivity here, or for the power here. And then the other one, you get the same I, you have the same length here, you have a 2 instead, and the area is 0.5 squared pi, so that means you get another 4 on the top, you get a pi on the bottom, and then you can just add these two up. So 9 times 4 times 3 over pi plus 9 times 4 times 3 times 2 over pi. It's 100. There you go. All right, next one. 9-volt battery, yada, 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 yada. We want conductivity, right? And the idea here is we're given X, we're given a certain dV. So let's start with the conductivity of section 1, right? Length over area. Is that what I care about? Yeah, same cross-sectional area. So here, it's different conductivity. So here the conductivity for the section 3 is like 1 over 3. And that will be times the length, which the length here is 4, like as literal as it gets, over area. And that equals the resistivity. We don't get the full resistivity, but we get the voltage. So let's try and relate it with the voltage as well. So the resistivity is equal to V over I. V here, it's actually the difference in V, so it's 2 over I. And you can notice that the two things we have here, A and I, they're actually constants between every part of the thing, so we can just leave them. And I mean, what this kind of allows us to do, as long as I'm not missing a term, is it allows us to solve for like the A over I term, right? If you just like throw A over there, you can get it equal to 4/3. Which then, if we kind of use the same idea here, what was I doing? I forgot. Oh yeah, we want 1 over the conductivity, which is equal to the length, which is 3 over the area, and it's equal to the difference in voltage, 3 over I. A over I, we just get, or sorry, this is not 4/3, this is 2/3. And then if you simplify this, you just get A over I is equal to 1 over sigma. So the conductivity is the inverse of this, 3 over 2. And final question, we have 2 wires of the same material. We want current density. So current density is in joules. Make sure you know that. And we can apply this formula here. Joules, it's equal to current over area. So we have that, we have that. Man, I'm losing my brain cells right now. But we don't have current, right? However, we can solve for current. Current is V over R. So we get V over RA. Now let's look at what else we're given in the question. We're given lengths. So let's try and relate with lengths. They're also the same material, which means their resistivity is going to be the same. So R is equal to resistivity rho L over A. So A V rho L A. A's cancel. We just get this voltage over rho L term, right? Okay, so let's see. The current density is 200 when the potential difference across it is 6 volts. We're going to see solving for rho here because they're the same material. Length of the wire A is 3 long. So rho here becomes 6 divided by 3 divided by 200, 0.01. Again, that's not to the correct magnitude probably, but I don't care. And when we plug this in for the new ones, we plug in 3 volts here, 3 volts, divided by 0.01, and also divided by wire B, which is 1 long instead of 2. And yeah, these are just complete red herrings here. You don't need them. So 3 divided by 0.01, it gives you 300. We're done with this exam.